Hello and welcome to Fighting the Silent Killers. My name is Daniel Alessandri. I work for the Power Generation Group at Paul Corporation. It's really my pleasure to welcome you here today, and for the next 30 minutes or so, we'll be discussing the problems associated with water and air contamination in power turbines, lubrication, and hydraulic fluids. Once the presentation is done, we'll have a little Q&A session, and I'll try to answer as many questions as I can today. And for those that we do not have the time to get to, we will gather up all the questions and answer and distribute them all to all the attendees that are present with us today. So in the next 30 minutes, a little over that, I'll be giving you a short introduction first, talking about some of the symptoms that may be signs of contamination and how they can impact our operations really on an everyday basis. We'll discuss more of the technical aspects with the origins, the behavior, some of the consequences of water and air contamination in the system. And we'll have a quick overview of the typical solutions that exist today in the market, and I'll try to give everybody a good sense of some of the pluses and minuses and how each of these technology could be used and in what circumstances they perform the best. And then finally, we'll conclude with a few key remarks, and then we'll move into our questions and answers. Now, as I said earlier, if we can't answer all the questions today, for sure, within a couple of days max, all of the attendees will receive a complete set of the Q&As that were generated today. The title of this presentation talks about silent killers, and it refers to the fact that water and air contamination will tend to act upon oils and machines over time. And even though the effect may not be immediate or immediately obvious, what you see on the slides are typical symptoms or statements that can be easily related to problems with water or air contamination in lube or hydraulic systems. So if any of these statements sound familiar to you, or maybe more than one would, then it's probably time to ask ourselves a couple of questions, and one of them obviously is to check whether we don't have a contamination problem in our system that's kind of running out of control. Where can water and air come from? What's the origins of that contamination? Well, it's mostly a case of breaking and entering. Both water and air will find ways to ingress into our system. Anything from heat exchanger leaks or other leaky components will facilitate the ingression of both water and air in our systems. During the operation of the machine itself, you have conditions that are favorable to water appearing, if you will, in the system. Things like condensation in the reservoir, or even byproducts of some fluid treatments. Things like ion exchange treatment, for example, that may use a wet-packed resin, can release water in the system. Of course, one of the most dangerous times in terms of ingression of water is during maintenance. So having good breathers on top of the tank, making sure that the leaky components are fixed as soon as possible, tracking any type of leaks through a heat exchanger or steam seals. These are all preventive measures that will help mitigate this ingression of both water and air in turbine systems. Like water and oil. So before we go any much further, I think there are a few concepts that we need to remind ourselves of if we are to understand further the type of damage and reaction and behavior that a mixture of oil and water may have an impact on the system. Some of them are very obvious, and the first one is a very intuitive concept. Water and oil don't mix. Now, you can shake a mixture of water and oil very hard, and what you'll end up with is an emulsion that over time will separate. So the natural stable tendency of water and oil is to almost be two different phases. Because they have different densities, usually the oil density is lower than that of water. Usually that means that the water will drop at the bottom of the sample or the tank. Water and oil have different viscosities, about 30 times the viscosity of water for typical turbine lube oil. That is important to remember because when we start mixing the two together, we'll see that it has a very strong impact on the overall viscosity or the lubricating capability of the fluid. And finally, something very important is some of that water can dissolve into the oil. And that phenomenon is usually temperature dependent, a little bit like coffee and sugar. So sugar will dissolve into coffee to a certain extent, and if you exceed a certain limit, then you basically find coffee at the bottom of your cup. So we'll get back to that concept in a second. That's a concept that we'll push a little further here. What you see on the left of this slide is a very simple chart that relates the fact that water in oil can be in two different states, dissolved and free water. And the separating point is called a saturation point. And that point is dependent on the temperature of the oil. So that usually when the oil goes up in temperature, it will have a tendency to dissolve more water into it. So in a sense, this saturation point tends to go up. It is significant learning because there is a maximum amount of water that can be, I guess, hidden or dissolved into the oil. This process is reversible so that when the oil cools down, then some of that dissolved water will actually come out of solution, if you will, get back in the form of free water, and that's where it appears in a sample as this cloudy sample or even a separated sample if you have too much of that free water reappearing. So it does depend on the temperature, but it also depends on the fluid that we're talking about. Not all fluids are created equal, including how they saturate with water. So on the right side of the slide here, you'll see examples of a few different fluids. Notice, though, that in general, as temperature goes up, most fluids increase their saturation level. So regardless of whether you're talking about an EHC phosphate ester fluid here shown in the blue curve or our typical mineral turbine lube oil in red at the bottom, the absolute values are very different, but the trend of the saturation point going up with temperature is quite a fairly general phenomenon. Something to remember, though. For a given fluid, this curve could change over time because the fluid will age, and as it ages, things like oxidation or contamination sometimes will have an impact on how much water can be dissolved in the oil. And typically, again, an oxidized fluid or an older fluid will have a tendency to accept more water in a dissolved form. So in the sense, as the fluid ages, its saturation curve has a tendency to move up. So now that we've discussed where the water comes from and its behavior when it mixes or not with oil, we'll discuss the effects and consequences that water contamination will have not only on the fluid but on the machine itself. One of the main problems with water is that it will increase the rate of oxidation and the rate of acid formation in the fluid. What's interesting to know is that this phenomenon of oxidation or acid buildup is very dependent on the overall cleanliness of the fluid in terms of metallic particles that are present in the fluid. Metallic particles such as iron or copper will act as catalysts to this oxidation and acid buildup process. That's clearly shown on the table you see here. For example, in line 2, if you have water but the fluid is free of metallic particles, then there is some oxidation. The final neutralization number, which is a reflection of the acidity of the fluid, may go up to about 1, which is bad enough. But look at what happened on line 4 or 6, for example. When you do mix metallic particles with water, within a very short period of time, the acid number will jump up, in this case to 8.1 or 11.2. So this clearly shows that both metallic particles and water act together to really create a big corrosion problem in the system. If that happens, your corrosive environments will be very detrimental to the health and the reliability of things like bearing and all the metallic components in the system. Second thing, and I mentioned that earlier, the presence of water in an oil has a tendency to decrease its viscosity, and it's not very difficult to understand intuitively. You mix a low viscosity fluid with a high viscosity fluid, overall you tend to degrade the lubricating capability of the oil. Therefore, by extension, you degrade the ability of the oil to maintain this oil thickness, separating metal surfaces in a pump or in a valve, or more importantly for us, in a bearing. We do need this oil to sustain tremendous amounts of load pressure and maintain this thickness. As you reduce the viscosity of the fluid or you add water to it, you really compromise the thickness of the oil film, and that's where you start seeing your abrasive wear increasing, you start pitting metal surfaces, and you start increasing the rate of bearing fatigue. At the bottom of the slide, you see the result of a study performed by FAG, a roller bearing manufacturer, along with Paul. And FAG wanted to quantify the impact on the life of bearings of water contamination. And the results are quite striking. As you can see on the slide, as you go up to dry level at the left of that curve, your relative life expectancy of the bearing shoots up tremendously. And notice that it's not linear. So that improving your water level from 1% to 0.5% level will not get you much in terms of bearing life. You really do need to get levels of water content that are much lower than that. Here I speak of total water, obviously. And beyond bearing problems, really all the components in the system will suffer from similar problems related to decreasing in oil film thickness. And in the example here, you can see what happened to two types of pumps, where we can measure the wear rate of pumps by looking at either a drop in volumetric efficiency in one case, or directly by measuring the amount of material that is being shaven off the pump surface, in the case of the vane pump. What you notice is when the fluid is contaminated with particles, of course you will wear out. And if you measure the reduction in efficiency, you find this 8% reduction in the case of a dirty but dry fluid. Now, if the fluid is both contaminated with particles and wet, then you see that the reduction in volumetric efficiency shoots up all the way to 33%. Similar result in the second example, with the added clue that this phenomenon does depend on the oil type itself. So in the example of the oil X, adding a certain amount of water, in this case 500 ppm, may double the rate of wear of the pump. And on the other end, with the oil Y, it will dramatically multiply the wear rate. So water and particles are definitely detrimental, and they will act in different ways depending also on the type of fluid we're considering. One other damaging effect that the water will have on the fluid itself is when it interacts with the additive package. In some cases, for some additives, water can react with the additive package and basically drop it out of solution. So you lose on both counts. You lose the utility of having the proper additive content in the fluid, and on the other hand, you start forming things like gels and sludge, which will have further impacts on the system. Things like plugging filters prematurely. So you'll see the life of the filter element go way down. Because what you're trying to do there is, instead of stopping particles, which is its real job, you will be asking the filter to start separating gels and sludge, and everything will be nice and sticky and gooey at the filter location. Not only at the filter location, but that phenomenon tends to plug the tight oil passages in the system. It will restrict the flows in some areas, and it's really something we need to avoid. And additionally to forming gels, you also have the better chance of growing bacteria in the fluid. That will also play a part in restricting the oil flows or plugging filters. And finally, water is a known promoter of air entrainment and therefore increased foaming in the system. So overall, we can definitely conclude that water is a major cause of reliability problems in power turbines fluid systems. So as much as water is a problem, air will act as the accomplice in the degradation of the fluid. Air will promote fluid oxidation and acid buildup, and therefore the byproduct of that reaction will start forming sludges and gels, as we've seen previously. It's responsible for cavitation and microdieseling, and that is really a big problem because wear rates will increase dramatically. It will wreak havoc on things like pumps and other components. Not only the components will be affected, but in the case of the microdieseling, the fluid itself is basically burning from the violent compression of air bubbles going through high pressure zones such as downstream of a pump, but also at the bearing sites. So these implosions of air bubbles will create temperatures in excess of about 1,000 degrees. That's how a lot of the varnish precursors, for example, are formed in the system and will wreak havoc in the system and accelerate all the degradation processes. The fluid becomes compressible because air is compressible. So in the case of hydraulic systems, where the goal is to impart pressures directly into moving components, you end up spending energy basically compressing air. So you lose controls, you lose the ability to fine-tune operations and flow rates and so forth. Overall, you lose the operability of hydraulic systems that way. What you see here are a few pictures of the reservoir and the foaming at its surface. As nasty as it looks here on the pictures, really the real damage happens within the system when this fluid is carrying air bubbles throughout. Overall, efficient control of water and air in fluid system is really critical to the health and reliability, availability and productivity of power turbines. So this next slide presents a concept that I think is very important for us to understand. What this shows is a typical oil saturation curve for a given fluid. And we show on this chart a couple of temperatures. Let's assume that you're talking here about a standard turbine lube oil system. So you start at the reservoir and you pump the oil to the bearing going through an oil cooler. And we'll first look at what happens at the reservoir location, because usually that's where most of the treatment will happen. So the temperature at the reservoir here I call the initial oil temperature. And in the reservoir, your water content exceeds what you think is reasonable, so there is treatment to be done. So let's say your water content starts at 0.1, much above the saturation point of the water in oil. And you decide, I'm going to get rid of all my free water by using a standard technology like a centrifuge or a coalescer that we'll discuss in a few minutes. If that works perfectly, what you'll do is move from 0.1 to 0.2. To go below 0.2 is almost impossible with a classic free water removing technology. Therefore, as we cool the oil when we move it from the reservoir through the cooler and on there to the bearing, then we move from 0.2 to 0.5. The total water content remains the same, but the main difference is now at 0.5, most of that water is in the form of free water. So in a sense, it will appear as if free water has been created almost out of nowhere. What happened is that this water was expelled from the oil phase as the saturation point dropped. So this is the fundamental reason why our real objective should be to take the water content from 0.1 all the way to 0.3, which is a very dry level much below the saturation point of the oil. If we do that, even cooling the oil from 0.3 to 0.4 will keep the water content in what I would call the safer zone, which is a zone where there is no free water being formed. This phenomenon shows why if you only control free water at the reservoir, you run the risk of forming free water downstream of the oil cooler and really sending that to the bearings, with all the consequences that we have discussed. It is critical, therefore, to take the water content inside the reservoir much below the saturation point. So we are sure that at any cooler point in the system, no free water will be, quote-unquote, created, if you will. So now it's time to discuss typical water removal solutions that exist today. And we'll start with a few basics. One of them is the liquid-liquid coalescer separator. This is a well-known product to basically force very small, minute droplets to accumulate within the coalescer and then exit the coalescer as bigger droplets that can be easily separated through what's called the separator. What you see here on the picture are the two elements of a typical liquid-liquid coalescer, with on top the coalescer proper and at the bottom the separator. The main advantage is it's very easy to use. It is disposable, so it acts and behaves almost like a filter. So put it in a vessel, let it do its job, and then once it's spent, you take it out and replace it. The big drawback, however, is that it cannot remove dissolved water. That is a process that will remove free water only out of the oils. It does need replacement, so There is a cost associated that needs to be accounted for. And of course, it does not remove any gases or air from the fluid. One of the most common methods to remove water from oil is to use a centrifuge. Its concept depends on the difference in density between water and oil. So when you think of a sample that you leave alone on a table, gravity will act differently on water than it will on the oil. That is why, naturally, the water will drop at the bottom of the oil sample. Now, by applying centrifugal forces to the fluid, what we simply do is really multiply this gravity force, and we create rotational Gs. In doing so, we can basically separate free water from the oil phase fairly rapidly and fairly efficiently. It is a well-known principle, and one of the main advantages is that you can process quite a bit of flow. It's a process that will be efficient at removing bulk amount of free water. However, it will not be able to remove dissolved water. And because it's a rotating piece of machinery, it tends to be relatively expensive to buy and relatively expensive to operate. It usually needs quite a bit of maintenance and fine-tuning to reach its desired efficiency. And finally, it has no way of removing dissolved water, but also no ability to remove gases, no air. One of the easiest ways to remove water from mineral oil is to use an absorbent media filter. So a hydrophilic material that is pleated in a filter format that will absorb free water as wet oil passes through the pleats. It's obviously very easy to use, very simple, probably one of the cheaper options to buy, but it has serious drawbacks. One of them is its limited capacity. If you exceed its capacity, you run the chance of releasing water back into the system. Contrary to the coalescer example we just saw, you're not actively removing the water from the system. You're actually keeping the water trapped in this filter, if you will. So you do run the chance of releasing it back into the fluid. The previous three solutions had one thing in common, and that is their inability to control dissolved water. On the other end of the spectrum, you can use flash distillation unit, which basically is to apply high temperature and high vacuum to the fluid so that we can basically evaporate the water away from it. It is very efficient. It does remove free and dissolved water, which is a very big advantage, as we've seen. On the other hand, because you need to apply very high temperature and quite a high level of vacuum, it is very energy intensive and quite expensive to operate. And if we are concerned about the long-term health of the fluid, we need to be aware that you run the chance of degrading the fluid thermally by either evaporating the lighter end compounds from the fluid, or you can actually burn some of the hydrocarbons and basically cook the oil. So not too good for the long-term health of the fluid, and high operating costs are really the major drawbacks of this technology. It's quite rare to find it applied on turbine lube oil. Very often you don't really need to have such a fast, I would almost say violent treatment, because usually what you need is safe and ongoing treatment. And that brings us to the concept of mass transfer oil purifiers, which is a machine that we'll use also in recirculation in the tank. But contrary to its distillation counterpart, we are going to use much lower vacuum and almost no heat input. This tends to make the unit much easier to use and safer for the oil, and also much cheaper to operate than its distillation counterpart. The result is still the ability to remove both free and dissolved water and also free and dissolved gases. So air problems can be resolved or remediated with a mass transfer oil purifier. It is a slower process, so that's one drawback. And also, varying designs mean varying efficiencies. Not all purifiers are created equal. The real secret to a mass transfer purifier design is to maximize the exchange surface between a very thin film of oil entering a vacuum chamber with a flow of dry air. If those two meet together, then you will be able to drive off very efficiently the water, both free and dissolved water, away from the oil. The real key is how well you can increase this exchange surface between the oil and dry air. It's not just about the vacuum level and certainly not about temperature. It's much more about the hydrodynamics of the process. So the vacuum tower inside such a unit is not just an empty space to bring in vacuum or heat. The internals make all the difference in the sense that they will force the oil to basically expand its surface area. And that is the key success factor to a design. It makes the choice of a good purifier a little more difficult than your basic distillation unit, which is basically about heat and vacuum level. In the case of a mass transfer purifier, it's much more about the components and the internals of this vacuum tower in order to really make the exchange surface between wet oil and dry air as large as possible. This is a typical illustration of the performance of such a mass transfer purifier. If you assume that we're working here with a typical turbine lube oil, then you're looking at the fluid that should saturate at 60 degrees at around 200 ppm. So you see on this curve that within 30 to 40 passes of a certain volume of oil through the machine, you can drive down the water level much below the saturation point. In this case, we're much below 100 ppm, for example. And we know that's important because we can keep the oil in this quote-unquote safe zone so that even when we start cooling the oil through the cooler or through the lines, then we're still making sure that we're not generating free water in the system. So even though different purifiers, different designs will have different efficiencies or different reliabilities because of their components and internals, overall the mass transfer concept for oil is considered to be probably the best compromise between cost of operation, efficiency, ability to remove dissolved water and gases, with the safety of the process because we're not adding any heat to the system. The quote you see on the slide is just an illustration of some of the statements you'll often hear from the oil companies themselves. So in conclusion, water and air will wreak havoc on both the fluid and machine components, so they do need to be controlled. But controlling free water is certainly not enough, and we've seen why. One of the key reasons is that dissolved water will turn back into free water as soon as the oil cools down when it circulates around the system. Preventive measures can make a whole lot of difference, and they are the first line of defense. Things like air breather or fixing leaks, or ensuring that we don't ingress too much humidity when we open up the system for maintenance, for example. All these little measures will have a tremendous impact in the ingression level of water in our systems. Solutions do exist for removal of both water and gas, but overall, mass transfer purifiers probably combine the best efficiency, reliability with a cost of operation and the simplicity of their use. And of course, their biggest advantage technically is that they will remove both dissolved and free water and dissolved and free air out of the system. And overall, water and air control is really a key part of any preventive maintenance program in power plant turbine systems. So on this note, I would like to thank all of you for your attendance. It's been a pleasure. I hope this was useful and informative, and we'll now open the floor for a few questions that we received during this webinar. So we've received a few questions. I'll try to answer some of them. So thanks to all of you who asked those questions through the Q&A box. One question from Jeff. What would cause misting out a breather from a reservoir tank? Well, breathers are there really to kind of control the moisture going into the reservoir. So the most common ones have some kind of desiccant material inside, and as the air is brought into the reservoir, it passes through the desiccant material. On its way out, though, because of course the reservoir breathes in and out, on its way out, some designs actually have a bypass valve so that you're not, quote unquote, using up your desiccant when you're expelling air to the outside. Now the problem with that obviously is this air may carry oil mist, and that's the case where you'll end up having oil mist emission away from the reservoir. So that's really a function of the design of the breather itself, which is not really there to capture what's going out of the reservoir. There are some technical solutions, and they are slightly different than a typical air breather in the sense that they act as what we call a liquid gas coalescer. You know, I mentioned in the presentation the idea of liquid-liquid coalescers, but you can also remove moisture and mist from an airflow in that case using a liquid gas coalescer. So standard breathers are not liquid gas coalescers, and therefore you have a chance of having oil mist coming out of the reservoir. But there are technologies to remediate that if that's the case. So thanks, Jeff, for that question. Mike asks, can you combine two different treatment methods for water removal? And the answer is yes, and you'll find actually systems, I guess the most common combination, if you will, would be to use a liquid-liquid coalescer separator to take care of a bulk amount of free water, along with a mass transfer purifier that really picks up the load as you reach saturation and really drives down this water content way below the saturation point. So it is possible. It's possible to add one after the other, put them in series, put them in parallel, depending on exactly what you want to do. In some cases, operators will start one and not the other. For example, you have a big ingress of water all of a sudden because one of the steam leaks has failed, and then you get this huge amount of free water coming in. Then you may just want to use for a while the coalescer part, and then keep the vacuum oil purifier, the mass transfer purifier for a continuous treatment. So there is a possibility to combine one or more of these solutions for water removal, for sure. Basic question from Ian is, can we contact you after this presentation? So what I will do here is actually send everybody before we're done, my personal email that you can definitely reach. So keep an eye for my email coming through about right now across everybody's box. So it's simply Daniel Alessandri at europe.paul.com, and I just send it to everybody. So that was the easiest questions of them all, I guess. So we have James asking, what happens if you don't have dry air available to use in a purifier? That's a very good question, very interesting question. What happens to air coming into a mass transfer purifier? It comes in an area of vacuum, right? So typically the air will expand as it comes into the chamber. So depending on the level of vacuum, for example, the air will expand 5-fold. And as it does that, its relative humidity drops by the same percentage. And that is the key. So if we think of the worst case scenario, right? You bring it in totally humid air. You're sitting down somewhere in Florida in the summer, and everything is, the air is as wet as your swimming pool, basically. So if the air is totally saturated and coming in the chamber, because of the expansion, its relative humidity will drop down to 20%. So you have creating this 80% free space, let's say, in the air to capture some of that moisture. And that's in the worst case scenario where you have totally humid air coming in. So that's a very good question, and it's interesting to remember that you generate dry air just basically by applying vacuum to it. Another question from Dave. Can you explain more what macro-dieseling is and how it affects the fluid? So I passed a little quickly on this one because it's related to air contamination, but it's really a big potential problem. So I'll try to answer it as simply as possible, and please, again, use my email if we need to have further conversation. So imagine an air bubble that is sitting in a volume of fluid, and you're upstream of the pump, so you're fairly low pressure. And as you move through the pump, the pressure of the fluid obviously increases dramatically and very fast. So this air bubble all of a sudden is subjected to a lot of pressure. And as pressure acts on this air bubble, its volume is going to reduce. So the volume of the air bubble reduces so fast and so dramatically that all the energy that was contained in this bubble basically stays in the bubble. It's so fast that the energy does not have time to dissipate into the surrounding fluid. So what that means is this tiny micro bubble that has been compressed has now inside all the energy that the bigger bubble had in the low pressure section. And that means that temperature really shoots up to, possibly, hundreds of degrees right there at this minute location. And that's how you start burning the oil. So the more air bubbles you carry and the more air bubbles you subject to this increase in pressure, you'll end up really creating multiple hotspots in your system. And that'll happen, as I mentioned, across a pump. But as you go through the bearing, this pressure load, if you carry air bubbles in your film, your lubricating film, you'll end up creating, micro-dieseling effects right there at the bearings location as well. So a question by John: what oil purification system does Paul offer for large power generation turbine oil reservoir? It's just it basically is a question of size, right? So the bigger reservoir you have, the bigger the purifier will be. And when I say big purifier, it's simply a question of flow rate. So there is a practical method to calculate how big your flow rate should be. And it's a function of how many times you need to recirculate a certain amount of oil through a purifier. Remember that, in the example I showed in the presentation, you reach the level you want after about 30 to 40 passes of the entire reservoir of oil. So then it's just basic calculation, right? You want to do it, okay, in 2 days, I know I have to push this volume 30 times through my purifier. quick calculation. That'll give me the type of flow rates I need for my purifier. And usually, whoever, Paul, as well as other people making oil purifiers, have a variety of sizes that will meet typical sizes for most oil reservoir. All the way, we've had experience all the way to nuclear turbine type reservoir. So there's really no upper limit to what can be done, obviously. Let's go through a couple of other questions. Microdieseling, okay. Raphael has asked, well, a compliment and then a question. So thanks for the compliment, Raphael. It's a great presentation. Great. Will we receive this presentation? Now, this will be made available on demand. So this presentation, as I gave it, was recorded, and all of you, all the attendees, will receive a link to basically replay it or reuse it on demand. So keep an eye for that little memo that will give you the link to access this presentation in the future. I think I have time for one more question. Let's see. Okay, what is water? Ian asks, what is water's role in varnish formation? Let's say it's an indirect role. In the sense, we talked about all the things that water will affect. One thing it will affect is the presence of some additive package. And some additives are there as antioxidants, for example. But one result of severe oxidation of the fluid is the formation of those tiny, minute things we call varnish precursors. And these are the things that float in the oil, and when you exceed a certain solvency, they will start depositing on the surfaces. So it's not like water forms varnish for sure, but because water will promote oxidation of the fluid, it will indirectly promote the formation of varnish. And I would say for varnish, our experience is that you'll see them in high flow rate systems. There are many other reasons why varnish forms. Oxidation is one of them. The big other one is thermal degradation. And I mentioned that with microdieseling, but that also could happen if you go through let's say a non-grounded or not anti-static filter, for example, a fine filter, where you basically generate sparking in the system. So water's role with varnish formation is definitely there, but it's more of an indirect role. Okay, so I think that's all the time we have. I will keep a log of all the questions, including those that I just answered. And these will also be made available to all attendees. So whether you ask the question or not, you'll get the responses anyway. So on this note, it's really been a pleasure for me to have you here attend. Thank you all, and I wish everybody a great day. Thank you.